Hi, I'm Henry from the University of Edinburgh, and I will tell you about our paper on controlling traffic microstructures for machine learning model probing. The machine learning development process in many fields has followed this cycle, where models are proposed to address an initial problem formulation and are then numerically evaluated to determine the state of the art. Models are then examined or probed to determine where a model has its greatest shortcomings that need to be addressed, and also why the model has these shortcomings, before proposing improvements to the model that address these shortcomings. I want to emphasize both the probing and failure understanding steps here, and prominent examples of precise failure understanding and subsequent model improvements include ambiguous words impeding the coherence of translations, which was addressed by the introduction of now incredibly popular attention layers, the famous example of convolutional networks being biased to learn object textures over shapes on unprocessed images, or video enhancement models that don't generate object sizes consistently before the introduction of multiscale RAD encoders. The key difference between model evaluation and model probing is that model evaluation tells you about the overall performance of your model and helps you select the best model. Model probing, on the other hand, helps you understand how your model reacts to certain inputs, such as where and why classification fails. In this example, probing the model tells us that the model does not perform on inputs that has these orange characteristics. In network intrusion detection, however, we are consistently missing these two crucial steps of probing and understanding. Therefore, instead of a circle, we have a stream of new models being proposed that supposedly perform better and better, but do not address or understand any shortcomings of existing models. Mistakes are therefore not identified and repeated instead of being addressed. A reason for this is that today's network intrusion datasets are not very suitable to probe and understand model failures precisely. They lack extensive ground truth labels that describe the given traffic, and when compared to natural language data or images, network traffic is quite difficult to read. It is therefore hard to make targeted alterations, such as replacing a word in an input sentence. As the title suggests, this talk is about controlling and monitoring structures in network traffic using a tool called DetGen that enables us to better probe network intrusion detection models. Now a little overview of this talk. I will first give an example of how control and monitoring of traffic structures helps us to probe and improve a state-of-the-art traffic classifier. Next, we will examine what influences shape microscopic structures in traffic that we want to control, before taking a look at how DetGen controls and monitors traffic microstructures. Finally, we will verify the level of control or experimental determinism that DetGen is providing compared to conventional VM-based traffic generation designs. Our first case examines an LSTM-based packet stream classifier by Huang et al. That is targeted to detect SQL injection attacks. We train the model on the original dataset as well as on traffic with similar characteristics and corresponding labels generated with DetGen. We then probe the model with traffic from DetGen and identify possible correlations between misclassifications and particular structure labels. Even though the performance is not too bad, we notice that the performance decreases when latency in the network increases. To be precise, the model is becoming increasingly uncertain about the classification of SQL-injected connections, marked as purple here, and connections with multiplexed GET requests, here in green, under increased latency. We test this hypothesis by generating two SQL injection connections which perform the same activity and are otherwise completely similar, except that one connection was subject to high network latency and experiences several retransmissions. When we look at the classification output of the network during the packet processing, we notice that the model performs well when encountering some malicious behavior, here marked as green, but becomes uncertain when encountering packet reordering sequences, which are marked as bluish here. The output activation of the model approaches zero after the injection process, but indicating a malicious connection, but approaches a value between 0 and 1 after retransmission sequences. For the connection not subject to retransmission, the activation stays close to 0. My guess for this issue in the model is that there were simply not enough retransmission sequences present in the training data. When keeping this in mind, we can improve the model with a simple fix by removing these reordering sequences in a pre-processing stage. This improves the model performance significantly in the presence of latency, as shown here on the right hand side, and by a couple of percentage points in the overall evaluation. Now we take a closer look at traffic microstructures and the factors that shape them. We define traffic microstructures as short-term structures observable at a packet or connection level in the form of characteristic sequences of interarrival times, frame sizes, flags, etc. corresponding to certain activities. Here you see 3 packet sequences corresponding to an HTTP GET request, which show a strong sequential structure corresponding to this activity. These structures are often leveraged by state-of-the-art intrusion detection models such as DeepCore or Kitsune to fingerprint traffic or detect anomalous behavior. Traffic microstructures can be altered by several factors. Here we listed the most important ones. The conducted computational task and the corresponding application ultimately drive the communication between computers, and corresponding structures have been used for fingerprinting for a long time. The implementation of an application or protocol can also have large influences on traffic structures, such as different versions of TCP or QUIC, as shown here in a graphic by Marx et al., where we see large differences in the load distribution during request multiplexing. As we've seen in our example, network congestion can influence traffic streams significantly by altering interarrival times, affecting TCP's packet scheduling and leading to transmission errors. A bit more subtle is the influence of computational load, but it can influence the speed at which a host processes data streams and lead to curbing of transmissions. As shown on the right side, it can also lead to less confirmation packets being sent by a host under load compared to when not under load. Caching or other information storage mechanisms obviously affect the amount of data being transmitted to a client, thus affecting the number of packets being sent, as well as the response from the client. Lastly, the presence of background traffic in a capture can affect the observed structures on a flow level, such as depicted here, where FTP, HTTP and some unknown activity are all captured in the same 5-second window of a given host. Now we examine how DatGen enables better control and monitoring over these influence factors. DatGen is a container-based framework we developed to specifically generate traffic in a near-deterministic fashion up to the specified randomization of these factors. It provides ground truth labels on all of the discussed influence factors to provide a clearer picture of the generated traffic. Goals that are at the moment secondary for us, but that were important in the design of DatGen, are the modularity of DatGen's implementation and its ability to scale the generation for specific traffic types. DatGen is generating traffic using a variety of scripted scenarios. Each scenario contains a network arrangement of containers, for example an Apache server and an HTTP client communicating that perform an activity, such as depicted here. traffic is captured directly at the container interface, such as shown here and here, to avoid any background events or packet loss. Scenarios contain sub-scenarios that perform specific tasks, such as the sending or the retrieval of information, and also implement communication errors or authentication errors, etc. We simulate effects such as network congestion or host load with tools such as NetM and Stress, and we implement optional randomization of parameters at each stage. As shown here, we control traffic generation both within the containers here via a selected application tasked or the simulation of caching and the transferred data. And also outside of the container here with host effects such as load and memory and network loss and congestion. The script that governs the generation process also collects information of the specific settings at each stage and feeds them to the overall traffic generation log. For more details, I refer you to an earlier paper on DeadGen that we published in 2019 or to our GitHub page. We now look at how well this configuration allows us to control our structures in the traffic. In other words, how deterministic the generation process can be. A key question here is how much our containerized setup improves this control over traditional VM setups. For this, we performed an experiment where we generated several traffic samples of traffic with all of our settings held constant, and did the same for VM-based setups such as the one used in the popular UGR16 dataset. We then measure how consistent the traffic is across the sample, or if there are variations that we cannot control. We came up with a set of 3 metrics to measure this coherence at different levels. The first one examines overall statistics in each connection, such as packet sizes, inter-arrival times, the number of flags being present in the connection, etc. The second one measures the ordering and dissimilarity of packet sequences, which we restrict to the first 15 packets in each connection. The last metric measures the dissimilarity of sequences of connections coming from each of the hosts. In other words, if the same number and the same ports in connections are generated in the process in each sample. A more detailed description of these measures can be found in the paper. Here we see a comparison of the measured pairwise dissimilarities of the samples on a log scales for 3 different types of traffic, namely HTTP traffic, file sync traffic, and botnet CNC traffic. As we can see, dissimilarity scores are overall significantly lower for DeadGen compared to the VM setup. This is especially pronounced for the connection sequence dissimilarity, marked here in green. Due to the background connections being captured in about 24% of all samples in the VM setups, which were not captured at all in the DeadGen setup. The packet sequence dissimilarity is more close for both setups, albeit being a bit worse for the VM setup. The overall connection dissimilarity is, however, far more spread for the VM setup, at least for HTTP and file sync traffic. Now here we see 3 packet sequence samples for HTTP traffic, both for the VM setup on the right and for DETGEN on the left. As you can see, we observe more spread in the inter-arrival times in the VM setup here than for DETGEN, and also additional packets such as this one here, or differently sized packets such as this one compared to these packets here, being present in the VM setup but not in DETGEN. In conclusion, our paper demonstrates that targeted probing can be a valuable tool to identify model failures and improve model designs correspondingly. Particularly useful tools for this are the labeling of traffic structures to correlate them with misclassifications, and the control of these structures to generate both traffic suitable for broad probing and corresponding correlation analysis, as well as traffic with little variations suitable for the examination of the effect of specific microstructures. Just to advertise our own work a bit, the DETGEN tool is available for other researchers on GitHub under this link.